Hi everybody, welcome to another general interest Sharcnet webinar. The topic today is heterogeneous computing using Boost.Compute and OpenCL. My name is Armin Sobani and I am with Sharcnet based on University of Ontario Institute of Technology. And this is my email here, so if there is a question in your mind after this talk is over, you can contact me directly. So the outline of today's talk is, at first we have a quick introduction to Boost.Compute and OpenCL, then we switch to a tutorial, which you can find all the materials in Sharcnet GitLab server at this link. I'll show you the link at the end of the first half of the seminar again. But let's start with our introduction to Boost.Compute and OpenCL. Standard template library, or STL for short, is an important part of the C++ language today. It consists of 4 components: containers, iterators, algorithms, and functions. One interesting fact about STL is that if there is a parallel STL, is going to be a really good asset. Why? Because it's familiar to most C++ programmers, and having such a parallel STL thing actually simplifies porting existing applications to parallel architectures. Currently, there are 2 types of parallel STL available. One is C++ 17 parallel algorithms that is already there, but is waiting for some implementation. Actually, there are one working open source implementation from Intel that you can find at GitHub, and the other one is a SQL implementation of parallel STL, again available at GitHub. But there are also third-party C++ libraries, which you can use usually as a header-only libraries, which is Boost.Compute, the topic of today's seminar. And there are also NVIDIA's Trust and AMD's Vault. Actually, the Intel's open source parallel STL is available, and you can use it with both Intel compiler and GCC. And actually, I'm going to, in my next general interest webinar, is going to be about using how you can compile or use Intel's parallel STL on Sharcnet hardware. But in today's seminar, my focus is on Boost.Compute. So what's Boost.Compute? Boost.Compute is a C++ header-only template library for parallel computing. It's based on OpenCL, and it's available in Boost C++ library starting with version 1.61. What's OpenCL? As you might know, it's OpenCL stands for Open Computing Language, and it's an open standard for parallel programming of heterogeneous systems. The latest version is 2.2, but it's not available, as you know, most of the vendors didn't provide the 2.2 yet. For example, I think there is an implementation by Intel, but it's not 2.2. The good thing about the 2.2 version is that now you can use the C++ OpenCL kernel. The previous ones you should use or write your kernel using C99. So OpenCL, we use a computing system as consisting of a number of compute devices. And we have some terminologies here, which, for example, kernel are functions executed on an OpenCL device. And OpenCL actually works by compiling C99 code at runtime to generate kernel objects. This is different from, for example, CUDA platform, which actually the kernels are compiled before running the program. But for OpenCL, the actual compiling happens at the runtime because it's a cross-platform standard. And it can't, because you don't know on which platform your program is going to run, it's not possible to have an object beforehand. So the program is responsible for compiling the code C99 kernel code at runtime. But before we starting talking about Boost.Compute, let's see what's the main advantage of Boost.Compute over the other C++ libraries like that, I mean Trust and Bolt. Actually NVIDIA's Trust, because it's running on CUDA platform, is a little bit faster than OpenCL implementation, which is also available on CUDA. But the problem with that is it doesn't work with, for example, AMD GPUs. So it's not multi-platform. And the problem with AMD's board is again the same, only works with AMD CPUs and GPUs. But the good thing about Boost.Compute is that because it uses the OpenCL, it's not dependent on any platform. So you can run it on any system that has a working OpenCL driver. But one thing that you should notice is that for running OpenCL programs, you need two things. During the compilation, you need an OpenCL SDK or software development kit. This software development kit is not in one place. I mean, every vendor, for example, NVIDIA or Intel, may provide this SDK. As far as you have one of these SDKs, you can compile your code. But after compiling your code, when you want to run your program, you need also OpenCL drivers by the vendors installed on this target system. So when there is no such a device driver, which is like OpenGL or ICDs, it means installable client devices. So the good thing about ICDs is that you can have several ICDs on one system. So if there is Intel CPU and also NVIDIA GPU on your system, you can install both drivers from two vendors, and you can choose on which platform your OpenCL running. But let's have a quick crash course on Boost.Compute. As I said, Boost.Compute is actually, you can consider it as a STL for parallel devices. Once you develop your program using Boost.Compute, you can run it on any system that has a compute device with the OpenCL driver. It could be a multi-core CPUs like Intel and AMD. Both Intel and AMD provide the driver for their CPUs and also GPUs. It can be AMD, Intel, or NVIDIA's GPUs, or accelerators like Xeon Phi, or even FPGAs. The library architecture is that at the bottom of the system, it has a layered structure. Compute devices like multi-core CPUs and GPUs and accelerators are there. There is the OpenCL layer, which Boost.Compute uses. And Boost.Compute has two layers. One is low-level API, and the other one is the high-level API, which has the STL-like API, API-like containers, iterators, algorithms, functions, and also there are like C++11 random number generators and also lambda expressions. But these lambda expressions are not the same as C++11 lambdas. The syntax is different. So low-level API is actually an OpenCL C++ wrapper. It wraps OpenCL objects like buffer, context, command queue, etc. And it takes care of reference counting, error checking, and there are also some utility functions like, for example, functions for setting up default device, which is important. So an example of low-level API, if you want to iterate all the OpenCL devices available on your system using range-based loop of C++11, with this one-liner, you can do that. So, and print the name of the device. If you want to do the same thing using OpenCL, you need this much of code in C language, for example. So as you can see, it makes your life really easier. One good thing about low-level API is that there are some functions for getting the default device. For example, if you want to get the default device on a running system, we can use this function call to simply do that. And then using that device, you can create your OpenCL context and also the command queue using this line of code. And if you later want to print a device name, you can use this print a device name and send it to a standard out. The default device concept is something that is selected based on a set of heuristics and can be influenced using one of these following environment variables. So, for example, if you export this variable before running your program and set it to, for example, AMD Radeon, the default device is going to be AMD device or AMD Radeon. Or you can select a thing based on the device type. For example, there are three different types of devices for OpenCL: accelerators, GPUs, and CPUs. So if you want to only select the default device, which is a GPU, you can set this environment variable to GPU, and etc. But you can also selectively decide on which device your code is going to run. So, for example, you can iterate using the same loop like this one and find the devices that you are interested in and start to run your code there. At the higher level API, it's actually a parallel STL. So there are some containers, which the most important of them are vector, which has the same interface as std vector, and map view also important, which we are going to show examples of these two containers in our tutorial. There are also fancy iterators like buffer iterator, zip iterator, and so on. And there are also random number generators like the ones that you can find in C++11. For example, normal distribution, uniform integer distribution, and so on. But there is a wide range of algorithms, which you can see the list of them here. Those that are in blue are actually algorithms that are actually the parallel algorithms, which in the parallel world you have them. So it's unique to Boost.Compute. And in a serial version of STL, you can't find them. So let's have an example. For example, sort is one of the most common algorithms in any program. Most of the scientific codes, in one part of the code, you need to sort your data. So if you want to do that using the STL, this is the minimalistic code snippet. For you need to include vector and algorithm, then have your vector defined, and then pass it using the iterators, begin and end, to sort algorithm. If you want to do the same thing using Boost.Compute, the only thing that you need to change is to include the header for the algorithms. If you include this header, it includes all the algorithms, so it may take the compiling time increases. If you only want to say that, oh, okay, I need only the sort algorithm, you can selectively comment it out this line in blue and comment out the first one, so it compiles faster. But you can use the same std vector, but rather than using std sort, you use Boost.Compute sort. And there is a third additional argument, which is a queue. You can omit this queue, so Boost.Compute then uses the default device and command queue for running that. But if you want to specify on which device and command queue your sort running, then you can include it. In general, it's a good idea to not omit this parameter, but you can do that. Then it tries to run the sort on the default device and command queue. So what's happening here is that this line of Boost.Compute actually first turns this, this algorithm into a C99 kernel code, which is then compiled at runtime, and also transfers the whole vector from this container, which is a host container, to device, sort it out, and then again copy it to the original std vector. This version of or type of calling algorithm is only available for some of the algorithms. For example, sort. For the other ones, maybe the reason you need to first have a device vector, copy the host vector to it, and after the algorithm run, you then need to copy back that to your original or host vector. But for the sort algorithm, you can use actually std vector as an input, and the whole thing happens in the under the curtain or behind the scene. So a typical benchmark using host sort example that we are going to run it on the Sharcnet platform later. As you can see here, for the smallest size of vectors, which is, for example, 100,000 vectors, STL is actually faster. But when it reaches to the vector sizes of 1 million, then the Boost.Compute shows its muscles. So, for example, the red one is the result on CPU, and the orange one is on GPU. So how these algorithms work, as I said before, when you have an algorithm like Boost.Compute reduce like this, what actually happens, first Boost.Compute generate OpenCL kernels in C99 like this. Then this kernel is going to be compiled at runtime and produce OpenCL kernel objects, which then it actually runs on the compute device. You can also have some custom functions. Most of the STL and also Boost.Compute algorithms accept a function for their operation. So you can use this macro, Boost.Compute macro, to define your function. For example, transform algorithm is one of those algorithms that need a function. And if you, for example, want to add 3 to each element of your vector, you can define your function like this using the Boost.Compute function macro. And this one is the type of the argument. This is the name of the function, add 3. And this one is actually the input and input argument that you can add or do something to it and then return. And later, when you want to call the compute transform, you need to specify the name of the function, which is add3 here as an argument. So it's also, this macro also produces Boost.Compute function object, which this body of the function is checked during OpenCL compilation. There is also possible to specify, rather than using the Boost.Compute function, you can use lambda expressions. But as I said, these are not the same as C++ 11 lambdas. The format is different, but it's an easy way for specifying custom functions, and is fully type checked by the C++ compiler. So this one is actually a placeholder. You say that, okay, the arguments for, or the one that is passing to the function or lambda is named _1, and then later you can use that to add number 5 to it. So it's good for simple operations, but for more complicated ones, you may decide to use Boost.Compute function, for example. So having this, let's start with our tutorial, which you can find it at git sharcnet.ca/asopania/bc-tutorial. I've already have this. If you connect to this link, you can find the instructions about how to build the samples. We have currently 4 samples included in the tutorial. The first one is CLinfo, which tries to use this device iteration to show you some information about the available devices. In order to compile them on Graham, this is the instruction that I'm going to actually use that in a terminal. So the only thing that I did was making the whole thing using the CMake script, and now you can see that all 4 programs are compiled and ready to be run. But because I specified my home directory, I can also do make install to install all those software in my home bin directory. So you can, later I can just run CLinfo, for example, using CLinfo. So if I run it like this, it shows that on the current node, actually I use the salloc command to allocate a GPU node. So because of that, you can see I have two platforms here. One is NVIDIA CUDA, and the other one is Intel OpenCL. And but if I do that on login node, for example, let me show you. For example, if I go to login node using this, if I run it on login node, because I've installed, I can run it here. You can see there is only Intel Xeon CPU is available as a device. And there are some difference between the number of maximum compute units. Here, remember that if you want to switch to or salloc, the actual salloc command that I used, let me show you, is this. Let me copy and paste it here. Remember that when you are on GPU nodes, you can't ask for 32 cores because each GPU only access to 16 of the cores. So for salloc, you can use something like this. I requested for 2 hours and 100 gig of memory because it's a reservation. But for your case, you can stick to a lower one. So here you can see the global memory size for NVIDIA GPU is 12 gigabytes, the size of the memory of the device. But the maximum allocation is about 3 gigabytes. So your data or vector can exceed that size. But for the Intel CPU, the global memory is about 128, but I have access to only 32 gigabytes of that. So you can also check the source code of the samples here. For example, this is the CL info, which actually uses the range-based for loop to iterate through all the platforms and devices, and then uses this fancy tree outputting to print all the foundings. But the next thing that we are going to run is the actual sort algorithm, which is actually the same one as I showed you in the slides, but it tries to iterate all the available devices and run that, and also perform a benchmark, and then try to do the same thing using the STL sort and have the results. So as a program argument, you can pass the number of vectors that you want. We try to have a number of elements in your vector, which are going to be integers. It generates a random vector and then tries to sort them. So the default size for the sort, oops, the problem is that the name is the same as the sort command of the system. So I should specify the sort. So here the default number is 1024, which is actually, you can see the STL is actually faster. But if I specify 1 million to have a vector of 1 million integers and then sort it, you can see that Intel OpenCL platform is faster than the default STL, but the Tesla is the same. By going further, you can see the difference is becoming higher and higher. Now, NVIDIA CUDA is 38 milliseconds, better performing than Intel OpenCL, and both of these are better than STL. And put one more. As you can see, for GPU devices, which are parallel, data parallel devices, as you increase the number of elements in your vector, the performance is getting better and better. But it may be limited to the size of the vector that you can put in the GPU. So let's try with this one too. So as you can see here, the NVIDIA implementation gets a memory object allocation failure because it's exceeding that 3 gigabytes limit here, max memory allocation for that. If I compile the same thing on my Mac, here, let me show you the output of CL info. Actually, it's here. I have one Intel Core, 3.2 gigahertz, and one GeForce GT. And if I do the same thing, 1 million. Oh, and the thing is that this default running tries to have 3 trials on each run. So, and it reports the minimum timing. So if I want to restrict it to 1, because it has a problem with my driver, I can do that by specifying here the number of trials after this vector size. So here, actually, because the size is small, GPU has a worse performance, but I couldn't increase it here because of a driver problem with the OpenCL implementation on Apple or iMac. So here is the performance of that. But there is another sample here, which I try to use the same sorting, but using a so-called zero copy memory thing, which is available using mapped view of the Boost.Compute. What's that? The thing is, when you do the algorithm, actually the whole vector must be first copied to device, OpenCL device, sorted, and then copied again to the host memory. But if the OpenCL driver supports the mapped view here, you can actually, rather than doing that, you can use the BC or Boost.Compute mapped view to view your device vector, to have a view of that vector. And then if the driver is optimized for that, there is no copy process. That part of the host memory becomes available to GPU or this OpenCL device, and that tries to sort the whole thing there. So let's see what's the difference with that. Let me also switch to my home directory source one that I have. Source here. So here, if I do the mapped view and 1 million, and doing the same with sort to see whether there is a difference. So here, there is no much difference between the Intel and also for the GPU. But if I increase it, let me first sort and then map view sort. You can see for the GPU, the time is a little bit better than this one. But for the OpenCL, Intel OpenCL, it's not. So it shows that maybe the Intel OpenCL driver doesn't support the zero memory copy thing. But for the NVIDIA, it's there. So let's increase it one more. If we are this waiting here is for generating the random numbers. That one, it takes a lot of time. So, but actually when you have the random numbers, the whole sorting happens quickly. That's why it's in the order of milliseconds. So here, so the timing is really much better here for the GPU. So it's reduced to 23 seconds. Or no, maybe map view is, let me, map view was one less zero, I suppose, yes. So again, you can see no difference between the Intel implementation, but the NVIDIA version is a little bit faster than, and the rate is almost doubled. And for the last example that we have here, it's actually in my field. I try to complement a sequence of DNA here. This is the source code for that. Actually, we try to generate a vector of DNA sequence and then try to complement it, which all the A's become C and all the C's became A and the rest like this. But for this sample, I tried to use the random number generators, Boost.Compute random number generators to actually generate the random sequence directly on the OpenCL device. And then we have two Boost.Compute functions to call. The first one is for generating the sequence. The second one is for complementing that. So, and this is the algorithm here, which is called the complement. And we are also doing exact same thing using the STL. We try to generate the random sequence and then complement it. So if I run this sample, which is called DNA complement, and for example, starting with a DNA with 1 million base pair. So as you can see, even for a smaller size, GPU is faster. So even if I start with 100,000, here GPU and STL are almost the same. But if we increase it to higher numbers, we actually get really fast results. So here, as you can see, on CUDA, it took 0.3 milliseconds to complete that. On OpenCL Xeon driver, 0.83, and for STL 26 milliseconds. And we can increase it one more to see. So it shows that the whole thing is that by really small changes, if you had a C++ code that uses the STL containers and algorithms, but by doing a small change, you can make it run on parallel facilities of Graham or Sharcnet clusters really easily. Just changing some function calls and adding one parameter and also including some headers, your code can benefit from parallel computing really easily without much of the trouble. So here, again, you can see the performance is getting better and better by increasing the size. Here, the Intel OpenCL platform has a good performance too, but not as good as the NVIDIA GPU. The reason is that this Intel, one question here, why this same CPU doing better than this one? Because this one is a parallel version. It tries to parallel it using the 16 cores. That's why. But it's an easy way to do it rather than, for example, using OpenMP and other things. So that's all the things that I actually wanted to demonstrate here. And I think we are finished. So I think I covered all the things that I wanted to tell. The only remaining thing is that if you want to run your code on a GraviDI or VDI device, because the module system is not available there and only NICs is available, the only way to build the samples is using the NICs, which the instructions is here, is more or less the same. And another thing is that if you want to do some experiments with the OpenCL, Boost.Compute and OpenCL on Sharcnet platform, this tutorial is really good starting point, and it will give you a head start. The only thing that you need to change is just clone this repository and put your C++ code here and only change this CMake list and add the name of the C++ code here at the end, or remove these guys and add your name of the files here, your source code, and you're done. You can make that using the same instructions. So it can give you a head start for developing your Boost.Compute programs. That brings us to the end of this webinar. Thank you for your time. I'm ready for any questions, comments, or thoughts.